Hello everyone, welcome back to the second part of this week's lecture for machine organization and programming. Today we're going to be looking at bitwise operators. This is section 2.17 through 2.110 of our textbook. And again, some excellent example practice problems available at the end of that section. And again, what I want to do here is provide like a high-level overview that makes the book accessible. The book goes very deep into these things. Practice problems sort of require that. But in order to make that accessible, that's sort of the goal of my lecture here, is to introduce these ideas. All right, and again, so bitwise operations are going to be, math things we can do on an actual set of bits, a binary number in the computer. It gives us sort of a preview of the kinds of instructions that are available on the CPU, and it's also going to give us sort of a, we'll talk about speed. So as we write our own code, we can maybe take advantage of some of these things we learn to make our code run even faster. All right, and I've got a couple of examples as to why we might ever care about looking at something at as low level as bitwise operations when we're writing code. And those examples are first bit masks, where we may have a 4-byte integer, and I only care about one piece of it. And so a bit mask is a way to extract that information. And my example there is the packed integers from computer graphics. If we have red, green, blue, and alpha channels for a number, each of those are 1 byte. Well, rather than taking an integer to store each of them, which is wasteful, integer is 4 bytes, I only need 1 byte for each of the color channels, I can pack them all together into one integer with all 4 pieces of data. And very similarly, Boolean values can be represented as bit flags if I have more than one Boolean value for a particular piece of data, like a struct of some kind. Each Boolean value only needs 1 bit. And the smallest available data type in C is the 1 byte, a char or a char, a character. And that's going to waste 7 bits worth of data. So if I can pack more than one type of Boolean operation, or Boolean true-false value into one data structure, that's going to save memory. All right, so without further ado, let's go ahead, jump in, and begin talking about bitwise operations. Okay, so in C, we've got 6 bitwise operators that I'm going to talk about right now. The first is the OR operator, and that's just going to be the vertical pipe. The AND operator, the ampersand. The NOT is the tilde. The exclusive OR is the caret, or shift 6. Does not mean exponentiation in C. We also have the left shift and right shift operators, which are just the double greater than or double less than signs. Okay, let's take a look at how these work. And I'm just going to go through this with some examples. First, we need all of our numbers to be in binary, so 1s and 0s. And then here's my example. So if I have x and y, 1, 0, 1, 0, and I'm going to start with the top one. I'm looking at the OR operator. This is just going to take each of the pairs of bits in each position. So over here I've got the 0 in the B0 position and another 0 in the B0 position, and perform an OR operator on those bits and store that again in the resulting B0 position. So for an OR, if either one of these is a 1, it'll have a 1. Only if they're both 0 will it give me a 0. So in the B1 position, I've got 2 1s. That's going to be true, so we'll have a 1 there. Here we have a 1 in that position, so we'll get a 1. And here in B3, we have a 1 in the x variable, so that'll be 1 also. AND works exactly the same way. So in this case, instead of, if they're both 0, and we get 0, they have to both be 1 in order for this to be a 1. So both values must be true or 1, logical 1, in order to get a 1. So 0, 1 has a 0 right there, so that'll end up as 0. 1, 0 has a 0 here. So we're just looking at vertical columns in the same bit position. Now, how to just highlight here, I put in the numbers here. This is number 10, this is number 6. This resulting number really doesn't have a neat mathematical explanation at this point. To get there really doesn't make sense. There's not a lot of connection. So here when we did the AND, we get a 2. The other one we got a 14. It's 14, right? Yep. All right, yeah. So not a lot of connection. So the next one is the NOT operator. So this is the only unary operator here. Wait, that's not true. Shifting is also, well, it only operates on one variable. Right, so this is the only real unary operator. So in this case, I've got my example 1010. When I do the not operator, that's just going to flip all of the bits. It's going to take ones and turns them into zeros, zeros turn them into ones. It's the same as the ones complement. So in this case, I've gone from 10 to 5. Again, no real connection here. If we were to add 1 to this, it would be like negating the number in 2's complement, because that's how the machines actually represent the numbers. Okay, next up, the exclusive OR. What we're looking at here, again, I'm taking two numbers. If the values in the positions are the same, that's going to return a 0. And there they are, they're both 1. They're the same, that's going to be a 0. And if they're different, so if I have a 0 and a 1 or a 1 and a 0, those are going to be return a 1. So it's going to fill in with a 1 in those bit positions. I'm trying to think of an example where that would be useful. And I know I've used it in the past, but my mind is blanking right now. Sorry, guys. Let me just move on. So the left shift operator is going to take a binary number and just move all of the bits over to the left. So if I'm doing a shift by 4, it'll take all the numbers, shift them over 4 positions, and give me the new number. So this 0 right here in B3 ended up in B7. The 0 here in B0 ended up in B4. So 0010 ended up 0010. And it's just going to shift in zeros for the bits that were vacated by the shift to the left. The most significant bits here on the left, because there's not room to store them, they are just lost. So we no longer have that data. All right, so pretty straightforward. It works the same for signed and unsigned numbers. I should also mention that the left shift and right shift are not strictly defined by the guidelines for writing C. They're compiler dependent or system dependent. And the guys who write the compilers can do whatever they want here. This is the most common way that we'll see this, and this is the way that it's implemented on the CSL machines. Okay, yeah, so right shift. This is going to depend on whether we have a signed number or an unsigned number. So, and whether, when we look at signed numbers, whether it's positive or negative. So the first example here, I've got a signed X. This is going to be a negative number. I can see because I have a 1 right there in the first position. If I were to do my right shift to the 4 position, that's going to take these 4 bits, the most significant bits, and they're going to become the 4 least significant bits. Because this is a negative, it's going to shift in 1s all the way across here. I'll talk a little bit about this as an example in just a second. For a positive number, like this number right here, it's going to shift in zeros. So the 0, 1, 1, 0, the 4 most significant bits become the 4 least significant bits, 0, 1, 1, 0, and it's going to shift in zeros. All right, this is known as an arithmetic shift. It's just the name of it. I can't for the life of me remember that. I don't expect you guys to either. Just happens to be what it's called. All right, so one way to think about this is we're going to be shifting in whatever's in this most significant bit position. We're just going to copy it over. My phone's been dinging all morning. It's a lot like sign extension. Okay, and then for unsigned values, we'll be using a logical shift. And again, I can't remember the name. I have to look it up every time, so I don't expect you guys to either. But here's the idea. Because we're looking at unsigned values, we're just always going to be shifting in zeros. So I take my 1001. These 4 most significant bits become the least significant bits. Oh, I didn't get this lined up very well. I'll fix that before I put them online. And we shift in zeros. All right, guys. So all of these bitwise operations are widely used and can be implemented to write some very efficient code. I want to just give you a couple of examples where this is definitely possible and places I've used them in the past. All right, so first up, I need to introduce the idea of bit masks. Bit masks are used to extract certain bits from a pattern. So, let me just do an example here. If I want to extract the 4 least significant bits from this number, if I've got x1001, 0010, I'm going to get just these 4 least significant bits, 0010. That's what I want. So to do that, actually, pause the video right here, go look at those 6 operations and see if you can figure out a way to turn 1001, 0010 into just the 4 least significant bits. All right, pause the video, see if we can figure out, and then come right back. Okay, I'm back with the answer. It's pretty straightforward. We can use the AND operator to create a mask that'll clear some of the bits and retain others. So if I just look at this sort of bit pattern as a window, if I've got zeros here, it's going to block these because anything ANDed with a 0 is going to give me 0. So that's just going to cancel out all of these bits and turn them into zeros. And then if I look at the ones as if a window that I can see through, anything ANDed with 1 just stays what it is. So 0 and 1, when I AND it together, is going to give me the 0, again a 0, and this will retain the 1. So I'm going to end up with 0, 0, 1, 0, just like that. So that's all there is to it. Pretty straightforward. Let's do another example. So suppose instead of the 4 least significant bits, we want to get the 4 most significant bits. So I want to return, if I've got this number 1, 0, 0, 1, 0, 0, 1, 0, I want to return these 4, 1, 0, 0, 1, but I want them to be in the least significant position here. So I just want to grab these. I want to know that my number is 9 in this case. All right, so pause the video, think about how you might do this, and I'll be right back with the answer. All right, guys, I'm back. Take a look at this. We're going to do this in 2 steps. The first thing we're going to do is shove all of these bits, the 1, 0, 0, 1, over into the least significant bit position. So they're in the right spot at least. So if we do this, this number happens to be a negative number. There's a 1 here, if it's signed, that is. So it will fill in the first 4 most significant bits with 1s when we do that. The 0010 is going to be lost because it's going to get shoved out of a place where there's no bit to store that data. And we'll get the 1001 in the correct position. The next thing we're going to do, step 2, is to use the AND operator to create that mask that's going to cancel out all these 1s I just shifted in and retain the 1001. All right. Pretty straightforward. I just had to do it in 2 steps. I'm going to jump down. Oh, yeah, there's the answer, 1001. Jump down. I want to talk about packed integers for a second. And here's my example. This is where it's very common. In computer graphics, we're going to represent colors by 4 numbers, red, green, blue, and then an alpha channel to represent transparency. Each one of these is going to be 1 byte, so it's got values between 0 and 255, or 0 to FF. And alpha is going to represent the transparency, so 0 alpha would be completely transparent. 255 or FF is going to be completely opaque. That means we can see it. This is used for compositing. If I want to layer images on top of one another, I can do that with alpha masking. Okay, so here's the idea. I'm going to store all 4 of these bytes, because they're just 1 byte, into a 4-byte integer, and it's going to save me a bunch of space. That way I don't have to waste a full int for each one of these numbers. All right, so the challenge then is, how do I get out a particular value? So if I want to grab blue, so it's going to be red will be the 8 most significant bits, then green will be the next 8, then blue will be the next 8, alpha will be the least significant. So what I really need, so alpha is going to be B0 through B7, blue will be 8 through 15, green will be, 16 to 23, and 24 to 31 for red. So if I want to grab a particular color, if I want blue, I need to be 8 through 15. Over here, I was thinking, wow, I'm using green text. I shouldn't do blue as an example when I've got green text. And sorry to those of you guys who are colorblind, but here's the idea. I'm going to go ahead and grab bits 16 through 23 to extract the green color. And if in my green text here, I've got 0 red, there's full green, 0 blue, and it's fully opaque. I can totally see it. It's not transparent. So this is going to be my bit pattern for the packed integer for the full color. What I really want to do is extract just the green. It should be FF when I'm all done, or 255. So pause for a second, see if you can figure this one out on your own, and then come back for the answer. All right, welcome back. Here's the idea. We're going to do this in 2 steps also. The first thing we're going to do is shift this by 16 bits, and we're going to go to the right. So in this case, we're going to move, this is going to be 4 bits, 4 bits, 4 bits, 4 bits, and that's 16. So that will move this FF all the way over into the rightmost position. In this case, I'm starting with a leading 0 bit, so it's going to fill in with zeros. If this had been a 1, it would fill in with 1s. So once I get the FF over here in the rightmost position, the bottom 8 bits, I need to do a mask again, and I'm going to AND with 00000FF to just retain those bottom 8 bits. In this case, I didn't need to do that because it would shift in zeros, but I didn't know that. So I'm going to go ahead and do that anyway. All right, so there's the idea behind packed ints. Next up, I'm going to talk about bit flags a second, but I need to go make a slide for that. One sec. All right, I'm back. I made some slides for this. I'm pretty happy with them. So bit flags or bit fields are just a way that we can store Boolean data very efficiently. Boolean data is just a 1 or a 0 in C, true or false. I only need 1 bit for it. But C is going to use integers for that, so that's 4 bytes worth of data. I'm wasting all that space. If I wanted to, I could use a char and just only waste 7 bits. But here's the idea. If I have a lot of Boolean data to store, I can just use 1 bit for each piece and store that in an integer where I've got a whole bunch of these all lined up ready to go. So let's take a look at an example. Maybe this will make more sense. So here, I'm just going to declare a bunch of variables to use as my flags. So these are data that would, maybe represent a typical person. So they could be old or young. And I'm just going to store 1 shifted 0 positions into old. So that's going to be number 1. And then I'm going to keep track of whether they're employed or not. So again, I'm using Boolean data, true or false. So I'm going to take 1 and shift it by 1 position. And now I'll get 00010 or 2. And then for the rest of these, I'm a parent. I'm not married. I do not drive a Ferrari. Sorry, guys, this job does not pay that well. But then I'm just going to shift a 1 into whatever position. So this is my mask for each one of these different variables. So again, parent is going to be shifted by 2 positions into that spot. Married will be over here into that one. Drives Ferrari into the that position. Now here's the idea. Now I can create a variable that represents all of the data about me with just 1 statement. So I capitalized it. All right, never mind. Here's the idea. I'm going to create a variable Mike. I am 45 years old, so I'm older than a typical student. So we'll go with old here. I am employed. I've got a job where I teach this awesome class to you guys. And I am a parent. However, I'm not married and I do not drive a Ferrari. So I'm just going to list the things that are true for me. And that's going to shift a 1 into, I'm using the OR operator. So it's going to take these top 3 and OR them all together. So if I look at this, there's a 1 there. So that will be the B0 position will have a 1 in it. This will have a 1 in it. So the B1 position will have a 1. The top 3, there's a 1 there. So B2 will have a 1 in it. And then for the first 2 bits, B4 and B5, 0, 1, 2, 3 and 4, they are all zeros, so I'm going to get 0, 0. So 0, 0, 1, 1, 1 is a field that has all of this Boolean data talking about me. Now, if I want to use that, if I want to extract just one of these Boolean values from that, it's very straightforward, a single operation on the CPU. So if Mike, and this is the bitwise old, this will give me, so the old field is right here, 0001. I'm going to AND with that 0001. So all of those zeros are going to cancel out all the rest of these bits. And then when I do old, that's going to have a 1 here. So this will return a 1. And anything that's positive is going to be true. So Mike and old says, wow, you're old. That will be true. If I use the drives Ferrari, I'm going to be ANDing with the 1, 0, 0, 0, 0. So the 1 here is going to extract that 0, and I get 0. And the rest of the zeros mask out all of those. So in the end, that will result in a complete 0 for whatever's in my conditional when I use the bitwise and that'll be false. All right, so last up, I want to talk about multiplication and division. All right, now to wrap this up today, I just want to talk a little bit about a trick we can use to make multiplication and division go faster. So first, a little bit about speed. If I'm adding or subtracting, this happens very quickly on a CPU. 1 to 2 CPU cycles, depending on the architecture. I saw different measurements out there as I was looking up some data for you guys. However, multiplication is significantly slower. We're looking at 6 CPU cycles. So basically, multiplication is going to happen a lot like you learned back in elementary school doing the long multiplication. So I've got 32 bits multiplied by 32 bits. It's going to take each one of those rows, shift it over, I'm going to get basically 32 additions that I've got to do. They can do those in pairs, so it only ends up taking 6 CPU cycles to do that. There's some other technicalities here that can make this go much faster. Modern CPUs are pipelined, which means they can work on more than one multiplication problem at a time, and they can come up with an average throughput. If I've got lots of multiplications, like if I'm doing like a matrix multiplication or something, or I've got lots of numbers, or I'm doing it in a loop, it can do those more than one at a time and bring down this 6 on average to 1 on average. So this is a little bit of a trick. However, division tends to be very slow at 30 to 60 cycles. So this is a little trick we can use for multiplication and division by powers of 2, like 2, 4, 8, 16. Here's the idea. If I'm looking at multiplying 14 times 2, it's going to give me 28 in the end. 14 represented in binary, 1110. Okay, if I want to multiply that by 2, 28 in the end is going to be 00011100. Okay, so the idea is I'm just shifting these bits one position over to multiply by 2. And here's how this works. So if I write out 14 as the, what is this? The powers of 2 expansion. So I've got 2 raised to the 1, 2 raised to the 2, 2 raised to the 3. I'm adding all those together. So this will be 8 plus 4 plus 1 plus 2. Sorry, I misspoke, plus 2. It's going to give me 14. And 28, when I write this out, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, I add those up, I get 28. Hold on one second. Let me make another slide. Okay, here. I think this is maybe a little more clear. So I've got 14 times 2. Here's my binary or powers of 2 expansion of 14. When I multiply by 2, I can distribute this 2 into this summation here. So it's 2 to the 3rd times 2, 2 squared times 2, 2 times 2. And when I multiply something by 2, 2 times 2, that's just going to increase the power here from 3 to 4. So that's going to take that 3 to that 4 right there when I multiply by 2. And this is the exact same thing as shifting all of these bits to the left by 1. And it's going to be the same if I want to multiply by 4, I'm going to shift by 2 positions. If I want to multiply by 8, I'm going to shift by 3 positions. So just knowing this little trick, I can use this in my code anywhere I'm going to be dividing by 2 or multiplying by 2. Like if I'm doing a binary search or something, I'm going to be cutting my data set in half. I can use a bit shift operator there, and that's going to happen in 1 CPU cycle instead of this 30 to 60. Now in modern computers, they're very fast. You might never notice unless you're doing lots and lots and lots of division by 2 that I can get away from. But during the 70s, computers were not quite as quick as they are now. And this was an important trick. So you'll see this throughout older code. When you guys go get real jobs and you're looking at legacy code, you'll see this bit shift used for division all the time. All right, I think this is going to wrap it up for me. Yep, that was the last slide. Okay, so I'm going to go edit the video, put it together, and hopefully it'll be up before I have office hours. I'm running way behind schedule, so apologize for that. Hope everyone has a great day. Definitely stay safe and keep our sick classmates in your back of your mind. All right, have a great day.